Hi everyone, this is Srikanth. I'm presenting my final project for FEA class. I attempted to model the linear actuator driven by the ball screw drive. The main objective of this project is to identify the system that is caused due to the compliant characteristics of the parts. The model consists of three major parts. One is the screw, the ball bearings, and the housing. The effective stroke length of the actuator is 600 mm with max speed of 55 mm per second. The screw is of 16 mm diameter and 5 mm pitch. The ball bearings are of 2 mm in radius, and the housing is 25 cross 25 cross 25 cube. To model the screw, I extruded a circle of 8 mm radius. Then I did a revolve cut with pitch of 5 mm. I did the same thing for the part. First I made a solid extrude part of this, and then I made a revolve cut of the same pitch but with a slight bigger radius for the circle, so that it gives a little bit tolerance for the ball to slide. And I assembled the whole system into this, having 16 balls with a housing and the screw. Uh, the idea was to give a torque on this side, and so that the screw drive moves uh, relative to the velocity given to the screw. Uh, but the main problem with this was the amount of nodes that it's generating is very high. It is not in the limit of 1000. If so, to mitigate this problem, I made an other model. By simplifying this model, I in this model there are five parts in total. This is a screw. The total length of the screw is just 25 mm with the same diameter and the pitch, and there is a beam element for the rest of 575 mm, and the same ball that we have in the previous model, and as housing as previous model but with reduced number of revolutions, so that we'll be reducing the number of balls that we'll be using here. And an extra part, the slab that is connected to the housing, which represents the loading condition of the uh, actuator. So there are two materials in this. The first one is the steel, common steel that I used for all the parts, except for this slab. And coming to the second material, uh, the only difference between the first material and second material is the density. I purposefully increased the density of this slab. I want it to be 30 kg, which is prescribed load for the actuator that I am trying to mimic. So the final assembly looks like this. The 25 mm part is made of the screw, and the rest of the thing is made by the beam element. There was a correction to the radius and the length of the beam element, as I equated the moment of inertia of the screw and the beam, as well as the max deflection caused by the screw and beam when they are loaded in cantilever way. With that, I was able to calculate the radius and length of the beam that I needs to use here to have the same equivalent screw. As the assembly is set, the next thing that I did is the creating a step. I made a dynamic explicit step with time period of 5 seconds. And for the parts to have interaction between them, I made an interaction property, the type contact, uh, and I used the uh, general contact explicit for the as an interaction. Later, I set up the constraints for the model. I use the constraints for the screw to attach the screw and the beam. I use the coupling constraint, and for the uh, this screw to stay at its position, I used a reference point and I constrained it using the coupling constraint. Each ball is made as a rigid body using the rigid body constraints, and as well as I made this block as well as to the rigid as a rigid body to reduce the computation complexity. If it is a deformable object, it is the computation cost is higher. Then the housing is attached to the slab using a spring and damper system. And coming to the boundary conditions, I made boundary conditions such that uh, the screw rotates only on the z direction, and as well as rest of the parts translate only in the z axis. And using the angular velocity boundary conditions, I gave the velocity to the rp1, the uh, angular velocity which I will be giving it as an input to the screw, and I defined an amplitude that creates a noisy signal, which can be seen from here about tools. But yeah, so this is the input signal that I'm giving to the system, the noisy input signal, and I created a job uh, on the model 3, and when we run the job, it takes very long time, so I'm skipping the running part. And this is how the final output looks like. So the uh, noisy signal input is causing the uh, ball bearing house to move in the z direction, and due to that the end effector, the slab which is connected to the uh, housing is uh, displacing. And I plotted we can plot the displacement of this graph. I plotted it here. So this is the displacement of the slab in the z axis.